This is basically the crankshaft for this RX8 with the bob weights set up for their weight. Once they've been balanced, and take into consideration the oil, the weight of the oil, and the weight of all the seals. We'll set up the bob weights, and then go ahead and make the corrections on the actual counterweights. I already got the majority, like 100%, 99.9% of the work done. But there's something that I want to point out. When you start getting to the minutest amounts of weight, and I'm talking like 1/10 of a gram. If you want to get to that level where I actually have this rotating assembly balanced to less than 1/10 of 1 gram, what you do is when you're reaching for that 0.00 something, you just can't trust that you're going to make a drilling operation, a weight removal operation, and not go too far, not go beyond the point. So once we get the assembly where it's at about less than 1 gram, like 0.7 of a gram on either side, then I start making the difference. You can see from drilling. You see the big drill marks? When I'm trying to remove like 2/10, 3/10 of a gram, we'll go ahead and do it with a, what do you call this thing? With an air grinder. And with practice, you know how much you take, so you go a little bit, and you spin it again, and you spin it again. I got this thing down to right now where it's at 0.1 something, like 1.3, 1.4, whatever. I want it to 0.0 something.
You've always wanted to achieve that.
Exactly.
You finally have.
The absolute maximum.
I remember you were saying that rotor kicked your ass on this.
Yeah, we'll get to that. I just did a spin on this machine, and here we are, 0.09 exactly on both hands. And this is what I wanted to show you, that when you get to that the level where it requires just the most minute amount of correction to make it work. I'm going to spin it right now. Now these amounts are so minute and so immeasurable that it is very difficult for the machine to actually pick up the exact angle where it's at. And they will vary from spin to spin, but I mean, you're talking about 1/100th of a gram of weight, Look at this, 0.07, 0.08. You can't possibly get anything better than that. Most people, I was talking to a gentleman from Sweden today, and he was telling me that, once they get below 2 grams, like 1.7, 1.5, 1.3, that's acceptable. Let it go. And yeah, that's acceptable to a certain degree. How much life do you want out of the engine? How much you want to reduce your internal parasitic drag? You can have good enough, acceptable, perfectly suitable, but you can also have perfection. And in doing so, it takes a lot of time and effort. Now, the reason where I'm at is because I've actually have added, opposite to where the correction is necessary, I've added little tiny pieces of clay to make my corrections, to know that what I'm going to actually remove with the grinder is going to give me the results that I want, that I'm looking for. I have that little tiny piece on the front counterweight, and this little tiny piece on the rear counterweight. How much is that? Let's find out. It might be so light that it may not even register.
That's where you have to drill?
No, I have to drill opposite to the little piece of glaze, but let me mark it. This little piece of clay weighs 0.4 grams.
0.3. Oh, 3. Oh, 3 or 4.
Well, 3 or 4, exactly. So somewhere about 3.5. Now, why do I need that much? Well, it's real simple, because the distance for that 0.4 grams at a radius of this amount has less of an effect, because we're gonna be drilling over here on the operating radius. That amount would be that amount, but now that weight out here actually has greater mass, because you're taking mass times distance.
So you'd have to take less than 0.4 grams, like 0.2
Exactly.
grams or something like that.
Exactly. You know, basically what I have to do is just opposite to that, just kiss it with this and spin it again. Kiss it with
And
this,
what
spin it
happens
again.
if you go beyond where you?
Well, in the front, rather in the rear, you're lucky, because if you take a little bit too much out and you shift the weight over on this counterweight, you've got areas where you can take weight off of it and reshift the weight again.
Oh, but it's more work.
I'll give you an example. Oh, it's a hell of a lot of more work, but you know,
When you're this close to perfection, you know, it's like, because if you go beyond and you have to, you know, you're adding more variables when you're drilling in 2 different places and trying to get that spot back.
exactly. I wanted to show you a counterweight that I had actually done some corrections on, but you know, I've got plenty of pictures of them, so we can certainly add them onto. Oh, I know exactly. We'll just add some shots. I think I have one in my office that belongs to a customer. I'll go look for it, but I'm not sure. Let me check it out. But anyway, the point is this: that you can actually get these numbers and get total repeatability by when you're looking for the last 2/10. When you want to get below 0.0 something, then you know you would do it like this. Now let's go to the rotors. This was the most difficult engine I have ever had the, not gonna say pleasure,
Challenge?
chance, yeah, the challenge to balance. For starters, RX8 rotors are the only series of rotors that came from factory out of balance. Totally out of balance. Here's one. No corrections of any kind on these rotors. This is an RX8 rotor. Take any year, previous rotor from Mazda, from the factory, they come balanced. To what degree? What they consider acceptable, somewhere around 5 grams. Maybe 3.5, maybe 7.5. But somewhere in the middle of 5 grams is acceptable for a production engine, totally balanced. From the factory, they get it to a level that is acceptable for a road car, for a street car, and they go. They're automated. You take this same rotor in an RX8 variety, and it's out of balance. There's no corrections whatsoever.
Well, that's progress for you, right?
Well, yeah, exactly. The reason why
Look, the car wasn't meant to last over 100,000 miles anyway. They figure, you know.
The reason why they
Why go through all that extra trouble that you're doing to get it perfected?
Well, yeah, but you know what? There was a reason why they couldn't balance the rotors for the RX8.
They're so thin.
And no, well, besides that, they are thin, but it's that side exhaust port.
Right.
That side exhaust port, if you don't run the engine hard, and most people don't,
Right.
The minute that these pockets would get full of carbon, they'd start scratching the side housings like a cat on a leather couch. You know?
Yeah.
So to prevent carbon buildup that happens by the exhaust port, they eliminated it, and they live with it. They said, okay, well, we'll just do an extremely lightweight rotor, and you know, hope to put the imbalances beyond the RPM range that the average person is going to drive the car. So that's the reason why these rotors don't come balanced from the factory. This one particular rotor, well, before I even talk about that one rotor, what's this one? This is the rear, and this is the front. I don't recall much about the front rotor. Thank God I did it first. But as you can see, I don't recall how much it was out of balance. But as you can see, it required some here. I first drilled based on a graph that I've compiled, different size end mills and different depths for different weights. I first drilled it here, spun it again. It needed more in this corner, because actually, if you notice that this correction and this correction have been made, that means that the heavy spot was somewhere out here where there was no material to work with at all. So you have to compensate, you have to segment it, divide it by the operating radius, and average the amount that we want to lighten over here by taking weight off where there is material. It's complex.
You're not worried that this is going to build up carbon and scratch the inside?
No, because this is a race car.
Okay, so it's going to burn.
It's constantly going to be burning the carbon out. Never see a race car rotor carbonized. Right. It only happens on street engines. So anyway, spinning it, correcting, I overcorrected.
Oh, shit.
Okay, and it's simply because you know, to make these type of operations, you have to physically remove it from the mandrel, from the balancer, take it to the mill, make your correction, hope that you didn't go too far, come back again, and do it again.
Oh, because you weren't able to use that grinder tool. You had to go to the mill to...
Correct. The grinder tool is that spot right there.
Right.
Okay, that's when I'm already so close that all I got to do is remove tenths of grams to get it where I want. Both of these rotors are less than 0.2 of grams, so that's 0.2, something less, like 0.13, you know, something in that range is what these grams are at, these rotors are at. So I corrected a little bit too much, shifted the weight over, and then took this amount out over here. Finally, my final correction on this side was to kiss it there. On the other side, it required a lot less correction, but again, over here. But we're lucky in that respect, because this side has the gear, and you don't have too many places where you can take it out, so you got to get a little creative. The other side, without the gear, you can actually go inside the rotor and take it from the inside, which makes life a hell of a lot easier. You see right there?
Yeah.
So anyway, I did this operation, got lucky, got real close, had to touch it there with a die grinder, and boom, we're dead nuts on the balancing. I have the data, which I'm going to print, so when we make this video to show you that these rotors are, I'm starting to remember right now, I actually have them on my phone, the picture on my phone, like 0.15.
Holy shit. This is going to probably be one of the most balanced RX8 race engines in the world.
Absolutely. Well, I told the guy that, you know, I was going to go way out of my way to really do something special for him, because, you know, he told me what he was doing. We hit it off of the phone, you know, and he's been more of a gentleman than most customers, you know. So he just said, take your time and just do the best possible. He hasn't been pushing me to get it done by any given date, you know. That's why I was able to dedicate so much time to it. This rotor was about 7 grams out of adjustment.
Oh my God.
And it was relatively simple to correct. Maybe it wasn't 7, but it was in the 6s. It was close to 7. This one,
the evil twin,
the one that really kicked me where the sun don't shine. I spent 3 days on this guy. 3 days. This rotor was
3 full 8-hour, 12-hour, whatever days.
Yes, complete. And I'm talking days that I was going to like 1 and 2 in the morning. This rotor.
That's mad scientist stuff, man.
This rotor was off by 16 grams.
Holy shit.
But the bad part about most imbalances, everything is dual plane, unless, you know, like a car wheel. They put, you know, they spin and they put the weight. Sometimes they put weight on the outside, you know, weight on the inside, because as you spin the part, everything that spins has a natural imbalance, and you know, that's the RPM and this and that. But it's divided. It's divided between, you know, how much imbalance you have on one side and how much imbalance you have on the other. Anytime that you have a part that is 2.5 inches or wider, you get the best result if you balance it in a dual plane application. If you're balancing a racing flywheel where it's only that thick, then obviously you can't try to balance on both sides. You have to balance it like a 10-speed tire, you know, where it's so thin that you can only, and I don't know if you've seen it, but they add like a little fish weight on one of the spokes for the professional racers, you know. Yeah, a racing flywheel is paper thin. Well, I grabbed one, but it didn't look right. This rotor required. Oh, anyway, back up. Normally, when you have an out of balance condition, you might have on the part on one side the weight over here, and on the other side opposed, or maybe at this angle, or maybe at this angle, but never on the same angle. So that acts as a sling.
Shit.
You know, remember when we were kids, the little airplanes on a string, and you whee like that? Well, imagine if the weight on this part is concentrated on both sides in the same exact spot.
That's got to create some
it's
serious.
Going like this, woo, woo, woo. You know what I'm saying?
Yeah.
Instead of like, you know, if you have the correct a heavy spot here and a heavy spot here, it's got a wobble, but it's not that bad.
Right.
Having the weight on the same place, you don't have a wobble. You just have a, I don't even know how to describe it except a swinging swing.
Yeah.
You know what I'm saying? Had to be totally out of whack. Anyway, the rotor was 11 grams off on this side and about 5 or 6 grams off on this side. Again, I took pictures of all of that, so we'll edit them into the video. The gear side was heavy around here. There's my blue mark. That was a heavy spot. Okay? So, actually, no, let me back up. The heavy spot, the real heavy spot was right there, which corresponds to the part that we hogged out. I should have started with that. Okay? The heavy spot was here. I went ahead and I hit it with the end mill, took X amount out, required some more, and I did this operation and I went too far. The reason why I know that I went too far is because look at where the blue mark is at. Took just 180 degrees opposite to where I did a mechanical correction. Now I was heavy, otherwise I wouldn't have that mark. And I was taking out the amount. I shifted the weight over. It's taking out the amount with the grinder by just going meep, meep, meep with these little balls. And basically, you know, you start from the center and work your way out in order to shift the weight back to where it's negligible at that point. Okay? This was the easy side.
Oh my God.
This side, and it was the gear side. This side was off by almost 12 grams. It was 11 point something. Again, I have the pictures, and we're gonna print them, and you're gonna put them into this video. There was no way to take, first of all, these rotors are paper thin. And in fact, I have one here that somebody, this is an RX8 rotor, that somebody thought that they could lighten it, and they did a standard lightening operation like we do with all of our race rotors. Here's one right here. This is weight taken out on both sides. This is standard practice for a racing engine. Well, somebody had the bright idea to try to lighten the RX8 rotor without knowing how thin they are. Take a look at that. Blew a hole right through it, right through the other side. And he only went down 80 thousandths. You know, there's on these series rotors, we go down 150 thousandths of an inch. So he went down half this depth and blew a hole in it. So I went ahead and I cut it up so I could take real measurements of how much material I actually have. There's no possible way to take almost 12 grams out of this range, you know? So the lucky thing is that since we don't have the gear on this side, I was able to get a flashlight. I was able to tilt the head on the mill and stick an end mill with a round end on it, like a ball, and hog out this whole area to take the necessary weight out, because you don't have enough material to be able to do functions like, where's this brother to this one?
Right in front of you.
To do functions like this. That might take out 1.25 grams, but I had to literally remove 11 point something, almost 12 grams from this corner. And like I was saying, this rotor, this is where the correction was at. This rotor was off 12 grams on one side, 6 grams on the other, just going whoom, whoom, like this. So I was able to tilt the head and get in here and wipe out the webbing. Look at that. Well, let me see if we can put it like this. You know, this is as it comes originally, and this is after it's been machined. So I came in here and just went like that, took a swing, probably had it on and off several times until I got close enough to be able to do some final correction. And then the final correction was done by taking a little bit off over here and then finishing it off with these 4 spots. That with the ball, that depth, I may have moved that weight over a total of 0.3 grams, possibly, maybe 4, no more than that. So once you get your gross amount removed, the very end, the final touches to getting it to where I want, was basically done by hand. And it required these 4 little kisses here and this one here. Like I said, both of these rotors are at 0.12, 13, something in that range. But this one here was the most difficult rotor I have ever had to do. I spent more than 3 days on it. It required so much thinking and
rotary kung fu
and analyzing. Well, you know, you're dealing with a customer's part, and he expects you to do it right. Had this, and you have to do it right, otherwise you end up destroying the part and having to replace the customer the part. So why?
Yeah, there's no room for error.
Yeah, there's absolutely no room for error. Had this amount of correction been on this side, I would have had to call the guy and said, I can't do it. Okay. It's just no possible way to take out 11, 12 grams of dead weight right there. Just your startup material.
Yeah, right.
Got lucky that it was on the side without the gear.
That doesn't cause any ill effects with the oil that flows in those grooves and stuff, in terms of cooling the rotors.
No, not at all, not at all. I've actually, I have a rotor for one of those 4-rotor engines that I ended up taking. I got 4 rotors, brand new. 2 rotors were within grams of each other and in static weight, and the other 2 rotors were within grams of each other. 2, 3 grams, 4 grams maybe. But this group and this group had a difference of over 200 grams.
What?
Almost half a pound.
No way. How is that
I'll
possible?
show you right now. Because there's 5 series of rotors in any family. Whether it's RX8, whether it's Gen 2, Gen 3, low compression, high compression, GSLSE, whatever. They have different weights when they make them, when they break the molds and machine them, at whatever weight they end up coming out, they have A through F.
Oh, that's right.
Each letter is worth 50 grams.
Okay, yeah.
So they can, when they can grab 2 C's, 2 D's, whatever, and you know, the engine is going, the 2 rotors are going to be within a range. Highly unlikely that one rotor would be at the upper end of the range and one rotor would be at the dead bottom end of that range, so that would be 50 grams, you know, between the 2. You know, you grab, on average, you grab 2 rotors, and both of them are gonna be in the mid-range, in their 20s, you know, 30s. So the difference between the 2 might be 6 grams, might be 10 grams, but it's not gonna be 20.
Right. It's that acceptable range.
If it is that much, they can just go back, put them back, and grab another set.
Yeah.
Match them up. That's how they do. I mean, I've seen videos of the factory, and this is, everything is there for the, you know. So they try to do from the factory the best possible job. You know, they can just take them to weight. Okay, these 2 are close. These 2 are not close. Grab a different one. I've actually opened up some engines that the rotors were within 2 grams of each other, static weight. Now the rotor spins at 1/3 the RPM of the shaft. So to a certain degree, the rotor itself could be more out of tolerance than the counterweights, because they're not spinning as fast. So if there's an amount of weight, which, you know, from what I've been able to see from doing countless stock engines, their acceptable tolerance is about 4 grams. You know, some more, some less, but that seems to be the range. These RX8s are just totally out of whack.
Is there a difference between balancing a rotary engine and a piston engine? Does it matter as much for a piston engine? Or?
A piston engine is 10 times easier to balance than a rotary engine. Far less work. Far less work.
Where do you balance it, on the crankshaft?
You would think that because they have so many more moving parts, it's going to be more difficult. But it's really basic. You weigh all your pistons. Your lightest part is your target. You take 4 pistons for a 4-cylinder, V8, 8 pistons. You weigh them all. Okay, this one here is the lightest one. So the rest of them, you basically get a die grinder by hand and you grind inside. I mean, if you buy quality pistons, they're going to be off by a few amounts, a few grams. Not going to be off by a tremendous, you know, they might be off by 2 or 3 grams. So by just grinding material away, strategically in areas where the webbing is thicker, you match the weight of the lightest piston. On the connecting rods, basically the same thing. You weigh them all, choose the lightest one as your target, and then you put it in a little fixture that has a fixed bearing and a scale on the other. So you weigh, you fix one end and weigh the heavy end, and then you reverse it and put the heavy end on the fixed bearing and weigh the light end. You do it to all of them. You pick the lightest one. Hopefully both heavy end and light end are going to be or rather small end and big end, are going to be the lightest. But what if they're not? You write down which connecting rod had the lightest small end and which one had the lightest top end, and you basically just grind with not even a die grinder, but a sandpaper, you know, on a grinder, just removing weight until you get them the same. Then you weigh them again. Now they're going to be much closer. Both big ends and small ends of the connecting rod are equal to each other. Now, since you've removed weight, you have to weigh the whole part again, and if whichever one is the lightest, you take material from the other ones from the beam of the connecting rod. Once you do that, you weigh the connecting rod, and those are relatively fast operations, because you're dealing with production parts, not casted parts, that are stamped, and they're all physically the same. So the changes are very minute, you know, and then you weigh them all, remove from the beam of the connecting rod, and that's it. You add the weight of the connecting rod, the weight of the piston, you add the weight of the piston rings, and a couple of grams of weight added for the amount of oil. And this is, you know, piston engines have been around since the turn of the century. This is data that is available. It's not a lot of trial and error and develop a black art for balancing a rotary engine. So once you set up your bob weights, which has taken into consideration what I just told you before, then, you know, you just, on a machine like that, you know, drill your front and your rear counterweights, whether they're external, whether they're internal, whatever. Balancing a piston engine is straightforward. On a rotary engine, you have to, if you have to do operations like this, you have to take the part off the mandrel, physically off the machine, take it to the mill, do an operation, come back, mount it on the mandrel, mount it on the machine, and spin it again. Whereas with a piston engine, once you have your bob weights made to what I just explained, you never have to remove the part. You just spin it, drill, spin it, drill. You know, that's it. With a rotor, you have to spin it, remove it, machine it, reinstall it, respin it, and hope you didn't go too far. So as your practice develops, a lot of the things that I do is basically, before I do any kind of operation, is corrected by adding clay, like you saw in that part, opposite to where it needs it, to see if the information that I have input into the balancer is actually good enough for repeatability. If it repeats the same results over and over and over and over, then you're confident that whatever you do, once you remove that part, it's going to take out that amount. But you have to double and triple check yourself, because if you trust your first spin without knowing that the setup is correct, you may have just, you know, let's say that it's heavy here, and you remove weight here, you just added more work to balancing this engine, because you shifted the weight to where it's already heavy. You see what I'm saying?
Yeah. You got to chase these invisible forces in rotaries. That's why it is a black art, like you said.
You're dealing with a lot of invisible shit. That's why I have so many rotors that are cut up like this, so that I can go in and weigh and, you know, and measure to see where there is material, where there isn't material. You know, you have to get very artistic and, you know, inch at it, little by little, little by little, little by little. Just, you know, at snail pace, you can get it to where it's like you just saw it. But make a big correction, you sometimes destroy a part. You know? But this, you know, the whole purpose of talking about these rotors, it was just that you could see where I had to go in there and hog out all that.
Yeah, I've never seen you have to do that before when balancing.
Not for balancing. For matching weight,
Oh,
yes.
yeah. All on, even on the other rotors?
Yes, like I'm going to show you one of these rotors that were almost a half pound different from the other set. How much I actually have to take out of the
four
inside.
rotor one? Yeah.
But basically, once you do the setup, you just go in there and you spin the part, go in deeper, spin the part, go in deeper, spin the part, remove it, weigh it. Okay, I got 50 more grams to go. Put it back in. This is basically you're reducing the weight without having to be with razor knife sharpness of where you actually do your operation. Basically removing a gross amount of material all the way around. You understand what I'm trying to say?
Yeah.
Versus actually removing a given amount of material in a given crank angle to be able to reduce the amount of imbalance that's in that area. Once that was done, I actually went slightly too much. Then across from it, I removed with a die grinder this little bit here, this little bit here. And that brought it into perfect balance. This was just absolute crazy. Because
how much would you say that was luck versus skill to do that?
No, I actually had this part on and off at least 4 or 5 times.
So it was just total labor, laborious work to get it there. It wasn't like you didn't get lucky at all with.
You can get lucky, and you know that comes from experience by making the right choice in the technique or the operation that you make. You can get lucky and just take out just the right amount on the first try or maybe the 5th try, but in this rotor, I spent 2 days or 3 days. It was just a gross amount of time. I must have had this part on and off, 20 or 30 times. Let me grab one of these suckers. Hopefully it'll be one of these top ones. Nope, not this one. These are rotors, balanced, lightened. See all these operations here, these operations here. They're much deeper. Even though I did these by hands, compare these to these. Right. These are craters. These are, ant holes.
Right. This is for that 787B race car?
Yeah. Okay. Again, this is a matching rotor to that for that 4-rotor engine. Lightened. Look at the amount of machining. I believe that I spent like a solid week doing these this rotating assembly. But this is the point that I want you to see. There was 2 rotors that were X weight. And then there was 2 more rotors, and each pair was almost identical to its partner. But the difference between this set and this set was almost a half a pound, over 200 grams. A half a pound is 225 grams. There's 454 grams to a pound. I had to come in here and go all the way around. See?
Yeah, I see the shiny.
You see the everywhere. So when you're doing an operation like this, it's much simpler because you set the machine up, you tilt the head, you go in, you spin it, go in again, spin it, remove an amount that you feel is substantial, take it off the mill, blow it all out, clean it all out, and weigh it. And then I say, okay, well, then I need to go, you know, a little bit deeper, or a lot deeper. But it's what it takes. You don't want to go so far that now this set of rotors is lighter than the set of rotors that were that didn't require lightening, because now you're, instead of working with 2, now you're going to be working with 4, and it can become a headache. But anyway, the point is that, and by that I mean the amount of time required to get this to work. The point is that I was able to remove by taking that amount of material, that depth all the way around, remove 200 grams out of 2 rotors, so that their static weight would match within grams the static weight of the other 2 rotors that were virgin, that were lighter than these. You understand what I'm saying?
Mm-hmm.
Where this operation is, there's a lot more to it. There's a lot less.
You left that piece on.
There's a lot less risk. There's a lot less involved, because you know you're just removing weight. Here, you're balancing.
And that rotor, that has that Ionetti seals on it and everything.
These?
Yeah.
Or the RX8s that we're talking about.
Well, both actually. I'm curious.
Well, yeah, I mean they're rotor race engines. You know,
Both have ceramic. 2 millimeter or 3 or what?
This one is 3. Yep. All my endurance engines run 3 millimeter seals. They're far, you know, the ceramic seals have absolutely 0 coefficient of drag, and so they don't weigh anything. They're so light. By having that radius curvature of the apex seal be wider, 1 millimeter wider, you would think it's not a whole lot, but it changes the arc of that radius from something like this to something like this. In the end, there's an infinite point of that arc which actually touches the rotor housing. But in actuality, in actual practice, that imaginary point of the top of that radius gets much wider, because the apex seal is constantly sweeping a certain amount of gasoline that's residual, that is in oil, that is stuck on the rotor housing. So the actual point of contact plus whatever it's dragging along or sweeping along becomes much wider. In doing so, the 3 millimeter apex seal is far more kinder to the rotor housing. It complies to the curves of the rotor housing much more, where a 2 millimeter apex seal, after X amount of hours, you know, maybe, well, from my ALMS days, we would see marks in the rotor housings after about 50 hours of use. Okay, as the apex seal crosses the minor axis, you could see and feel parts of the epitruncal curve have sharp segments to it. Whereas with 3 millimeter seals on the same type of peripheral port rotor housing, engines have logged 360, 370 hours of racing and practice. 3 seasons of running. Take the engine apart and the rotor housings are like brand new. So yeah, on an endurance engine, naturally aspirated, definitely 3 mil ceramic. No two ways about it. Turbo engine, depending on the boost level, I'll consider whether 3 millimeter is required or not. Depending on the fuel used and the temperature, there's a lot of factors to whether you want to go with a 2 mil or a 3 mil. But basically, the boost level is the number one criteria. The 3mm seal will actually generate a little more heat into the rotor housing. So you're putting a little bit more heat into the rotor housing and taxing more the cooling system. So, you know, there's just a lot of considerations to take when it comes to selecting an apex seal for a turbo engine. But very dangerous to tune or run, for that matter, or mainly tune a turbocharged engine on ceramic seals. I don't care what brand. It's not a very wise or smart idea, because the ceramics, it's like a diamond. You know, diamond is the hardest thing that exists, but you drop it on the floor, shatters. Same thing with ceramics. Okay, the ceramic is so hard, and so smooth, but it is that, because it's so hard, it's that brittle. So a shock load, a thermal shock load, or a pressure shock point of a turbo engine with a detonation, a pre-ignition, some kind of a ping. It's like you take a glass of fine china, ding, off the freezer, and you hit it, bing, and you can, you know, shatter it. Same thing happens with a ceramic seal. On the boost, if the tune is not perfect, you're bound to have a catastrophic failure. And when a ceramic seal breaks, it's like hitting the whole insides of your race engine with sandblasting.
Yeah.
It's absolute total destruction, including crankshaft.
Wow.
It just gets everywhere. Some people have gotten lucky and simply cracked them. Lost compression, and you know, they should have played the lottery that night. I've seen it. I've never seen it happen, but another engine builder, I saw it in his place, and the person, Dr. Iannetti, the guy that makes the apex seals, have told me that sometimes they've cracked and not jumped out of place. But if they shatter and become powder, or worse, like shrapnel fragments, throw it all away. There's no saving a single part of that engine.
Wow.
So if you're gonna use ceramics on a turbo motor, you basically have to tune it on metal seals until they actually bend and bow and lose compression, preferably a real soft seal. And then at that point, open the engine and switch to a ceramic seal and not touch the map at all.
Wow.
The problem is that you better have the best of the brand of equipment. New injectors, new pumps, everything clean. Because if you take a chance, you do that, and you take a chance on an old injector that may have some debris, run the thing for a week or two, and all of a sudden it starts flowing less with a ceramic seal inside the motor, it's going to get to a point it's going to lean out and bing, same thing. Too many factors in a turbo motor that can go wrong to chance it on a part that potentially could be so fragile.
That two-rotor, three-stage engine that you built for the Caribbean race team, right, did that have ceramics or metal?
No, absolutely not.
Because it's turbo.
That's got Rotor Aviation Super Seals.
Okay.
I would have used something a little bit softer, like an ENJ, which worked fantastic. But at the time, I used 3mm, had that engine, and at the time, Edgar didn't have any in stock. So the Rotor Aviation Super Seal is still soft. It's harder than the ENJ, but it's still soft enough to take an impact and not break and destroy half the engine. Another thing that happens with a turbo motor that a lot of people, they know it when it happens to them, but they don't consider it as a potentially dangerous and big expense, is that if you break an apex seal or shatter it, the majority of the time it'll break into several pieces, not just two, and by sheer luck happen to stay there. If a piece breaks, it's going to go right out the exhaust port and straight into the turbocharger exhaust impeller. So not only are you now looking at a rebuilding an engine or half of an engine, you're also looking at a new turbocharger. So turbo engines are very, very, very unforgiving. The slightest thing, you cannot oversee any one aspect of a turbo motor, or like a lot of people say, oh well, we'll build it as we go along. You can't do that with a turbo engine. You either go all the way from the first time, or don't do it, because it'll bite you. Unless everything is right, it will bite you. Fuels obviously are better. Somewhat of a band-aid on turbocharged motors and gasoline. You know, an engine running on ethanol, on E85. You know, E85 is available everywhere. They're spread out, but there's gas stations all over the place that carry E85. I'm now starting to see E100 available. That's even better. E85 actually has a higher octane rating than C16. E100 is way up there. You know, so this is a readily available, environmentally friendly fuel that can tolerate all sorts of stupid mistakes on the tuning and save your engine. Downside is that you burn twice as much. You burn 50% more from switching from gasoline to 40% more.
You know, well, that all too well with the Miata on E85.
From switching to gasoline to
that's
E85,
why you have two gas tanks.
You all of a sudden need about 40% more gas. And then add a turbo to that, and that foot, and you know, you got...
add another 50%.
Yeah, add another 50% to that, if not more. So all of a sudden, your fuel consumption doubles, or your driving range is reduced by 1/2.
Wow.
So, but anyway, we kind of got sidetracked. The main part of this video was to show, you know, what is required to balance an RX8 rotating assembly, and the fact that if you spend enough time on it, you can get it perfect, absolutely perfect. But it requires time, you know.
So would you say after this experience, it's better to go with the, you know, this 13B block with the low compression rotors if you're doing turbo, or the high compression if you're...
I wouldn't use an RX8 rotor unless my life depended on it. In other words,
okay.
if only if the job requires it, would I use an RX8 rotor.
After this experience.
A stock RX8 rebuild, forget a performance RX8 rebuild, that don't exist.
Right.
You know, all you can do is try to regain some of your internal drag and some of your parasitic losses by optimizing what is there, like by balancing, by cutting the grooves and putting some RX7 seals, the normal tall ones, instead of the tiny little RX8 seals that, you know, just in sheer volume of material, they're gonna be 10 times stronger. You know, you're comparing something that is this high to something that is, well, I don't have one here, but you know what a regular Apex seal looks like. Well, I'll show you what. This is an RX8 seal. This is an RX8 Apex seal. Here's the 2 indentations for the spring. And this is an RX7 3mm Apex seal. Both the 3mm and 2mm are exactly the same height. This seal is actually a little bit less height than a brand new one or an untouched one. The reason why I'm telling you this is because we've dressed the seal to reuse it again. But look at the difference. It's more than half.
Wow.
So, strength-wise, this seal is going to be 10 times stronger and more rigid than this seal. The reason why they had to do this is because they took the porting configuration on that RX8 engine so far out that it required moving the side seal on the rotor further out, and it required a smaller apex seal. They could have done what we do, which is basically cut it and cut a groove and put in the RX7 seal and use the RX7 corner seal. But we're building racing engines or performance engines that it's acceptable, it's expected that after one season or two seasons you're going to go through that motor, rebuild it again. You know,
you're not going for longevity
exactly.
on the seal.
And the RX8 engine, I mean, if it's a factory motor, they expect the thing to go at least 100,000 miles. Well, the corner seal has a little metal insert where none of the previous corner seals had that. Some of them had a rubber plug to aid in starting up. Reduce anywhere there where a little compressor could leak out. Where on the RX8, they had to plug it with a steel plug so that it could go by the exhaust port and not end up burnt, singed, or getting exhaust underneath the spring, causing premature loss of pressure. So, you know, why are certain things work and the other things work also, but you must use one versus the other? The application. If it's a domestic engine, domestic use engine that's got to last, you know, hundreds and thousands of miles, I mean, you expect at least 100. Most of them fail by, all of them fail by 130. All of them. And a good majority of them fail at about 70. Those are the ones that run hot. The ones that, you know, haven't blown up from running hot, they go 130. Then you gotta rip them down. They're all carbonized, all the springs are burnt out. The engine just retains so much heat versus the other ones by having the exhaust port go through the engine block. But you know, you can see that this apex seal is so much bigger than this apex seal. It's just bound to last longer. So you can take an RX8 engine and make improvements to it so that it lasts longer and take more abuse. It's not going to take more temperature because that's the O-ring, that's the water seal, and it's not going to make any more power. You just for whatever life it gives you, you're just going to have it be more resistant against, you know, wear and tear.
So for the average guy that's got an RX8 motor or plans to rebuild it, he doesn't want to do a retrofit like we're doing with the RX7 motor, is it worth it to do all the machining work that you're talking about here, or is it...
A racing guy like this guy that wants to have an edge on against his competitor, which has a bone stock engine too, yeah, he's willing to spend the money and try to find those 5 horsepower that got lost in manufacturing tolerances and this and that. If you could, this is a class where every car has the same stock engine, every RX8 anyway. But it's a what they call an IT class, improved touring. You can improve the suspension, you can improve the brakes, you can improve the exhaust, but you can't touch the engine. So,
when you say touch the engine, what do you mean?
Port it.
Can you do what you're doing though?
Yes.
Why is that?
Because you haven't done anything to alter the breathing capacity.
Okay. So it's just the motion dynamics of it, basically.
Now, realistically or technically, if the steward wants to be a jerk, he can say that you're cheating. But in a class like that, where you can tell that the engine is bone stock, you haven't altered the breathing capacity. Who's gonna point a finger at you and say, you know, your engine is not stock when it's running the same and it sounds exactly the same? Everybody knows that when these engines have any kind of work done to it, the idle quality changes and they get into that exhaust note. You know, so in a class where everybody's supposed to idle like, you know, a Lincoln Town Car. You know, and you got one guy going blah 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 blah. Well, you know that guy's cheating. there's no hiding that one. You know, but you can do some things to the engine to basically free up what it's actually consuming just working, and some modifications to the rotor housings to get rid of the heat, like the stuff that I did to the race engine. You can do all those things and get away with it. You know, and basically all you're doing is getting more and more and more reliability. Is it going to make any more power? You're going to lose, you know, if it's properly balanced, you're going to release a few ponies here and there that get consumed by the actual operation. You're going to release that. But you're not going to make 20 horsepower. No. Sorry, ain't happening. And anybody that thinks they can, they're kidding themselves. Notice how I am trying to be less vulgar.
Yeah.
Anyway, that's that.
All right, thanks.